Thank you very much for the invitation. We're sorry that we could not make it there in person, but it is wonderful that technology allows us to participate like this. So I have the easy part of the talk. I'm going to talk a little bit about some of the background material, and then I'm going to turn it over to Pico, who was one of several students working with me this past summer at a research program at Williams College. And so I'm going to assume everybody is familiar with the basics of L functions. What I want to do is I want to try to motivate the problems we're looking at. So the general situation is we have some system and we observe values at T1, T2, T3, and we want to try to figure out what rules govern the spacings between these events. And depending on what type of math or physics you like to do, there are many different types of systems you can study. You can study energy levels of heavy nuclei, you can study eigenvalues of matrices, you can study zeros of L functions. And what's fascinating is that these very different systems often have very similar behavior. And frequently what happens is each system has their own specific rules that allow you to do the calculations. There's a very similar procedure and recipe to do the calculations, even though the actual mathematics is different in each case. And what's wonderful is that one system can often suggest what another system should look like. And so even though the calculations are done differently, it gives you some intuition as to what to see, what's a good question to ask. So most of the problems come down to determining three things. The first is what is the correct the first is what is the correct scale to study the events. We want something that's going to have a nice limit as some parameter goes off to infinity. We want some explicit formula that's going to relate what we can study to what we want to study. And then these formulas would be useless if we didn't have a good averaging formula to then execute whatever arises. And this is where, unfortunately, number theory does not do as good of a job as random matrix theory. We just don't have as good averaging formulas. And so we'll be using the Peterson formula. Sometimes we use things for Dirichlet characters. But in general, for GLN L functions, we just don't have good averaging formulas. It's often not easy to figure out what's the correct statistic to study. The difficulty is trying to figure out what is going to be combinatorially tractable. And I'll talk a little bit more about that in a little bit. And so everybody, I'm assuming, has seen the Riemann zeta function. I'm one of the managing editors of the Journal of Number Theory. At least once or twice a week, we get a proof of the Riemann hypothesis that all the non-trivial zeros have real part 1/2. And it turns out that the spacings between zeros look like the spacings between eigenvalues of complex Hermitian matrices. Rather than looking at the Riemann zeta function, we could instead look at a more general L function. And for us, it's going to be very important that the L function have an Euler product, so we can write it as some product over primes. And again, similar to the Riemann hypothesis, we believe in this situation that all the non-trivial zeros will also have real part 1/2. And so there's lots of different questions where to determine what's going on in number theory, it comes down to trying to understand some information about the zeros and the distribution of zeros of these functions. To give a sense of how we get our hand on what's going on, one of the things you always do in complex analysis is you take the logarithmic derivative, and this is why we want an Euler product, because the derivative of a log is the sum of the derivatives. And then when we expand everything out and then we do a contour integral, then the left-hand side, the integral of zeta prime over zeta, we're going to get contributions from the zeros and the poles. On the right-hand side, we're going to get just these weighted prime sums. Instead of integrating against x to the s over s, we could put in a more general test function. And if we replace p to the minus s with an exponential, we see we get a Fourier transform. So this relates sums over zeros to sums over the Fourier transform. And we get what's called an explicit formula. And so the left-hand side, from the contour integral is going to just be I was just getting an echo for a second. Okay. So the left-hand side is going to just be a sum of a test function over scaled zeros, and the right-hand side is going to be related to the coefficients of the L function. There's a lot of different statistics people can study. In the interest of time, I'm not going to go through them. They're in the slides. If people have questions, I can talk about them later. And what I want to just focus on is a statistic that was introduced by Katz and Sarnak called the n-level density. And so we're summing over some test function phi1 through phi n. They don't have to be equal, and Pico might talk a little bit about that in a moment. And what's nice about this test function is because this statistic is because phi is rapidly decaying because it's a Schwartz function. Most of the contribution is going to come from the zeros near the central point, and arithmetically, we know that these are going to often be very interesting. Think Birch-Swinnerton-Dyer conjecture. And so again, most of the contribution from this is going to be the zeros near the central point. And the hope is that as something goes to infinity, usually the conductors, that this will converge to something nice. And this is the Katz-Steinach density conjecture, that the behavior of these zeros near the central point will look like the behavior of eigenvalues of a classical compact group. If you're looking at just the one-level density, it turns out that it's very easy to write down what the formulas are. This is quite misleading. As you look at more terms, as you look at the n-level density, these formulas become far more complicated and much harder to work with. And so we're going to just change notation ever so slightly to match a phenomenal work that was done in the past few months. The previous record had been doing the one-level density for support up to -2,2. This was broken to now -4,4. And so ideally, we would love to take for phi to be a delta spike. And if we could take a delta spike, we would know exactly what's going on at the central point. But unfortunately, the Fourier transform of the delta spike is the function that's identically 1, which would require us to be able to execute sums over all the primes, which we unfortunately just can't do. And so we're going to try to look at these n-level densities, or actually Pico is going to be looking at these n-level densities and trying to compute these for the most general test functions possible. The more test functions we can compute this for, the more information we can deduce about the zeros. And so I'm going to hand it over to him now.
Great. So yeah, as Professor Miller said, we're going to be studying a specific case. And for us, the first thing we need to define is a modular form of trivial Nabentypus, which is basically this function from the upper half plane to the complex numbers that satisfies this really nice symmetry property. And in this property, the second property is effectively saying, as you go off to infinity, this function is in some sense bounded. And what that tells us is that at infinity, f is one periodic, and so we can take its Fourier expansion. And we get these coefficients a, f, n, which a priori are just some complex numbers. Now, we can define a cusp form, which is just a modular form that happens to also vanish at all the other cusps of gamma naught q. And we denote by SKQ the space of holomorphic cusp forms. And by some Atkin-Lehner theory, we get this orthogonal decomposition, SKQ into old forms, SK old, and new forms, SK new. And our primary study is these new forms. And it turns out that a cusp form is an eigenfunction of these Hecke operators Tn for n coprime to q, and we get these coefficients lambda fn. Again, for now, these lambda fn's are a priori just some complex numbers. And it turns out that if f actually is an eigenform of more Hecke operators and also these involutions, then we say that f is a new form, and we can actually further restrict these to be what are called primitive new forms, where we have psi f1 is 1. And it turns out that what's nice about this is that the space of new forms has an orthogonal basis, which we can denote by HKQ, of primitive new forms. And so this is really nice because in some sense we can understand primitive new forms really well. And the relevant point here is this trivial Nabentypus tells us that these Tn's are actually self-adjoint, which by some relatively simple linear algebra tells us that these lambda fn's are real, which is useful down the line. Okay, so now if we have some new form, then we can define the associated L function to it by this lambda fn over n to the s. And this factors into as follows. But the nice property is that because these lambda fn's are real, as we said, we get that LSF is LSF bar, and this will give us some cancellation later on. And we can also, it turns out, extend this LSF from just the from a right half plane to the entire complex plane. And we have a similar GRH that tells us that the zeros, the non-trivial zeros, all have real part of half. Okay, so as Professor Miller mentioned, there's a bunch of different symmetry groups or symmetry families that a class of L functions or forms could satisfy. And it turns out that for this family, the correct family is the orthogonal group. And so what Katsarnak predicts is that if you effectively average over the one level density over HKQ, you should go towards this integral. And if we recall, this function for the orthogonal group is actually relatively easy to understand. And it's actually equal to, by some relatively basic calculus, phi hat 0 plus a half phi of 0. And these terms will appear later on. Okay, so what is the work that's been done previously? So in 2000, Waniak, Luo, and Sarnak proved the following result. So they assume GRH, as we all effectively have to do, and then they let phi be any even Schwartz function with support in minus 2, 2. And then they proved the Katsarnak density conjecture over square free levels. So there's two notable things here. One is that they proved it for minus 2, 2 support. Obviously, we want to effectively prove this for arbitrary compact support, but that's far beyond the reaches of what our abilities are currently. And it turns out that it's actually relatively easy to prove it for phi hat having support in minus 1, 1. That turns out to be not so bad. So they've effectively doubled it from minus 1, 1 to minus 2, 2. But they've had to add this additional condition that the level is square free. And this is just some technical condition that allows them to do some manipulations further down the line. So then last year, Balyut, Chandi, and Lee proved a result where they extended the support to minus 4, 4. So this is once again, doubling the support, and it gives you much more, nuanced and detailed information about the zeros. But they had to introduce additional averaging. So they introduced this psi, which effectively is just any compactly supported function, and this psi hat of 0 being non-zero is just to make things not cancel in ugly ways. And then they defined this further averaging where this bracket star, where you effectively average over a bunch of different Qs. And because psi is compactly supported, you're actually, for each big Q, you're only going to do this over finitely many little Qs. And then this NQ is just a factor that makes this turn out to be nice when you plug in 1 instead of this one level density. So effectively what they're saying is this: if you just average exactly what you expect to have over a bunch of different little Qs, then what gets spat out is exactly what Katsarnak predicts. So the key thing here is that they extended the support from minus 2, 2 to minus 4, 4. And previous to this work, people had done 2 plus a little bit, or from minus 2 plus a little bit to 2 plus a little bit. But they've effectively doubled the previous best, and they added a little bit more averaging, but we're going to be doing something similar. Okay, so as Professor Miller mentioned, the one often relevant metric for measuring these zeros is the n-level density. But it turns out that the combinatorics for the n-level density, as soon as n gets greater than 2, become incredibly difficult. In particular, one thing you would need to know is what percentage of the forms have sign +1 or -1. And this is just very hard to understand. You'd like to assume that it's a half, but it turns out that's not always the case. And so given that we don't have this detailed understanding of what percentage of the forms are odd, it isn't possible to do the n-level densities without having some terms left over. On the other hand, we can find something called the nth-centered moment, which effectively gets around all these issues, but you still get to do the interesting math past the combinatorics. So what we're doing here when we define the nth-centered moment is you take the expectation of what the one-level density is, which is this integral that by Balyut, Chandi, and Lee we have a very good understanding of, and then you multiply n of these together and take the average of that. Something notable is that previous work, including the Waniak, Luo, and Sarnak result, often split forms by their sign into +1 and -1, and this gives you a stronger result. But we can't do this because we need to use this averaging over the entire HKQ to be able to get our result. So we actually can't split by sign. Okay, so what's the primary result? So assume GRH, we need to add the additional restriction that psi is non-negative, which is innocuous. And we, instead of having all our test functions being the same phi, we're going to denote them phi, but it's the same. And suppose that they're all supported in minus sigma sigma for sigma less than the minimum of these two things. Then it turns out that this n-level density, the nth-centered moment is exactly this product or the sum of this product, and it's kind of ugly looking, but it turns out that the thing on the right is relatively simple and is relatively easy to compute for any n, for any test functions. And if you check, when you plug in n equals 1, we have this the characteristic function 2 dividing n, so that's just 0. So the whole right side dies for n equals 1, and for n equals 1 on the left, you're subtracting off a constant. So effectively what's going on for n equals 1 is we get the exact result back. If you plug in n equals 1 to this min, you can check that you actually do get 4. So our work is a generalization of the Balyut-Chandni result. Notably, for n equals 3, we achieve sigma equals 3/4. And it turns out that prior to this work, apart from n equals 1, the best known result was, in general, for the nth standard moment, 2/n. So for n equals 3, obviously that's 2/3. We improve that to 3/4, so just by a little bit. But it turns out that for n equals 2, we can do quite a bit better. As I said, the combinatorics only becomes impossible once n is strictly greater than 2. But when n equals 2, you can actually do the combinatorics. And so we have this result for n equals 2. Now, our result for n equals 2, if you check, if you plug into that min, if you plug in n equals 2, you actually only get 1. But if you take different test functions, you can allow the first test function to be supported in minus 3/2, 3/2, and the second test function to be supported in minus 5, 6, 5, 6. And then we can actually compute the full 2-level density. And this first integral is the same as the integral from above, but the rest of these terms are effectively the terms you get because you're doing the 2-level density, not the second standard moment. And this odd is the proportion of forms of the odd functional equation. This is just some constant. And this agrees with the predictions from random matrix theory. So the key relevant point here is that we have to take different test functions. If we take both of them to be the same thing, under this restriction, they would have to both be supported in minus 5, 6, 5, 6. Turns out that our result still holds for minus 1, 1, but it's only when you're allowing the test functions to be different can you actually achieve improvement. And this is something that hasn't been seen before. So if we're trying to, so in particular, if you add 3/2 and 5, 6, you get 7/3, which is greater than 2, which is better than the previous best of each sigma 1 equals sigma 2 equals 1, which is sum to 2, obviously. And more generally, we can actually pick, we have a whole class of these results where if you take sigma 1 greater than sigma 2, and sigma 1 is less than or equal to 3/2, with sigma 1 plus 3, sigma 2 is less than or equal to 4, then you can actually get the same result. And the above choice of sigma 1 and sigma 2 is the way to maximize sigma 1 plus sigma 2, which is in some sense the actual metric for how much understanding you have of the zeros. Okay, so let's sketch out some of the key ideas. So we can use the explicit formula that Professor Miller mentioned in some slightly different form to turn a sum over the test function against zeros into these first two terms, if you recall, are exactly the terms that are predicted by Katz and Sarnak for the 1-level density, plus an error term, plus the sum over primes. And so the error term is very easy to understand. This constant term is very easy. And so the main term that we need to care about is this sum over primes. And this is for n equals 1. This is very easy to understand, and Balyut-Chandni and Lee deal with this. So what we need to do is effectively combine any of these together. So if you just multiply any of these together and you do a bunch of arithmetic, the only thing that's a little bit annoying is that your primes can be the same thing. All you're summing over is primes that aren't dividing this q, but if you take 2 of them, their 2 primes can be the same thing. But it turns out that once 2 primes are the same thing, you get LFP quantity squared, and that lambda FP quantity squared, and that actually, by some GRH for LS and squared F, is actually relatively easy to bound. And so all the terms where you have 2 primes repeating, you can actually show that those are all small. And so we can reduce this sum to trying to bound the following sum, where we add on this additional condition that the primes are all distinct from each other. And what's nice about this condition where the primes are all distinct from each other is that these lambda f's also have a multiplicative property. So we can drag the sum over HKQ all the way through the sum and product all the lambda f's together. And so now we have lambda f1 and lambda f, the product of all the primes. And from here, we can use work by Ing to turn the sum over HKQ into a sum over BKD. So this is effectively, we have to do this to progress, but it's a little bit annoying because HKQs are really nice bases of primitive forms, but BKD is still an orthogonal basis, so that's relatively nice. I mean, it turns out it doesn't really matter which one you pick. And the thing is, we can't just do this for a single D, like Q. So we actually have to do this for all the Ds that are dividing Q in this weird complicated formula. And we have this arithmetic function thrown in. But it turns out that pretty much everything here is really easy to control, except this very last sum where you're summing over BKD. Okay, so what effectively is going on here is this is allowing us to use the Peterson intuitively it's the Peterson trace formula, where if you sum over an orthogonal basis of lambda fn, for m equals n, this delta of mn will be 1, and this sum will be relatively small. And so hopefully, it's a quasi-orthogonality relation. Because if m and n are distinct, this delta mn is now 0, and this sum is the only thing that you're left with. Now, this sum is very hard to control. It's a Bessel function against a klystrom, and these things are sort of weird oscillatory things that, like, ideally we extract a lot of cancellation from, but in practice, it's really unclear how to extract any real amounts of cancellation from any of this. And so bounding this sum is like the main task that actually the remainder of the paper does, where you're trying to use a bunch of tricks to not take a naive bound on it. And the naive bound spits out effectively the trivial bound of -1,1, as I mentioned previously. Okay. So if we put x to be the product of the primes, essentially what happens after we apply this formula is we get a bunch of terms at the front. V is essentially a smooth and compactly supported function, so it's easy to understand. And PIs are just, big PIs are just constants. And so the main thing that, again, we have to deal with this is sum over blue, the blue sum over S. And it turns out that this sum is pretty ugly, but because H is compactly supported, we can actually apply the Kuznetsov trace formula. And what's nice about this is that we've effectively done a lot of work, and then we got to truncate this Bessel function, but we can do it in a nice way such that all the truncations and then that we sum over are compactly supported. And what that spits out is something that we can apply Kuznetsov's trace formula to that will further simplify it later. So in some sense, we've done the trace formula, we've done the Peterson trace formula, and after some manipulations, we do another trace formula by Kuznetsov. Okay, so Kuznetsov turns this blue sum into sums over 3 terms, the holomorphic cusp form terms, Moss cusp form terms, and the Eisenstein series terms. And it turns out that these 3 terms were the same, Bayut-Chandy and Lee get these same 3 terms. And the holomorphic cusp forms and the Moss cusp forms, they deal with relatively quickly. And by similar techniques to what they do, we can actually do them in generality for n primes. There's additional complexities, but we do, for those 2 terms, actually do get the full 4 versus n for restriction on sigma. However, the Eisenstein series terms are not so simple. There's some result that tells you explicitly what they are, but it's very unwieldy as the number of primes gets more complicated. So just some remarks on where we get the restrictions on sigma. So if you check this above manipulation, this sum over C is technically, if you look at the details, that actually deletes Q. Q doesn't really exist. So this is kind of abusive notation, what I've written. And so what actually needs to happen is you need to remove this restriction that the primes don't divide Q, because at this point, they're just prime numbers. They don't really, there's no Fs existing anymore. The issue is that for n equals 1, you only have to add back the ones where P1 are dividing Q, which is log Q many, which is relatively small. But when n is greater than 1, you have to add back where P1 divides Q and all the other primes don't. So you have to add back an exponential amount in Q as opposed to a logarithmic amount, or a polynomial instead of a logarithmic amount. And so this results in this first restriction on sigma, the 3 halves over n minus 1 term. And for the Eisenstein series terms, we at some point want to do a contour shift, but it turns out that the signs when n is even can be opposite each other, and so you actually get no cancellation in that case. And so that reduces us back to the 2 over n case. When n is odd, we do get a little bit of cancellation, and that's why when n is odd, we can do a little bit better than just 2 over n. So yeah, we'd like to thank these people and the NSF. And thank you. And if you have any questions, please ask.